In the next 2 lectures, we will develop a method for analyzing Galois groups using reduction mod P. Our goal is to prove the following theorem. Let f be a monic irreducible polynomial in z of x, and let p be a prime number and we consider the reduction of f mod p, which we'll denote by f bar. So here we reduce each coefficient of f mod p. So this will be a polynomial in zp of x. Let f bar is equal to f1 times f2 times fr. And so let be a factorization of f bar into irreducible factors of degrees d1 ... dr over zp. So this means that in z of x, the original polynomial is irreducible, but when we take the reduction mod p, possibly this polynomial will factor into irreducible factors. Suppose all factors in these factorizations are distinct. So this means that fi is different from fj for I different from j. Then the Galois group of this polynomial over rationals, which is a subgroup in the group of permutations Sn, where n is the degree of our polynomial f, contains a permutation which is a product of disjoint cycles of lengths d1, d2, ... dr. This theorem says that we can extract important information about Galois groups by looking at reduction mod p of the polynomials that define the extensions. By varying the prime, we can get information about possible cyclic structures of elements of the Galois group. The main technical difficulty in proving this theorem is that the Galois group is defined for field extensions, and we cannot reduce fields mod p. For example, reduction of Q mod P is not well defined because of the issues of having possible zeros in denominators after we reduce mod P. To circumvent this abstraction, we have to work with rings and not fields. And here, the tool of integral extensions will prove to be indisposable. Our basic setup is the following. So we have R is a domain. F is the field of fractions. Of R. Then E is the Galois extension of F, and S is elements in E integral over R. So the diagram is that downstairs we have our domain R and its field of fractions F. And upstairs we have a ring S and a field E. So S is the integral extension of R and E is a Galois extension of F. The most important example for us is when R is integers and F is rational numbers. So this is what we should keep in mind. The point of this construction is that for the field E, we cannot do reduction mod P, but this can be done for the ring S. So what we need to do is to understand better the structure of ideals in the ring S and their interplay with the action of the Galois group of this field extension. We begin with a simple lemma that says that in the above settings, E is the field of fractions of the ring S. Let alpha be an element of E. We need to prove that alpha can be written as a fraction with numerator and denominator from S. Actually, we'll prove something stronger, that the numerator of alpha will be from S, but the denominator of alpha may be chosen from the ring R. Our field extension E is Galois, so this tells us that alpha is algebraic over F. But F is the field of fractions of R, so this means that if we have a minimal polynomial of alpha over F, then we can clear denominators and obtain a polynomial over R. So this tells us that alpha is also algebraic over R. Let B in R be the leading coefficient of the minimal polynomial of alpha in R of X. We know that if we multiply alpha by B, and let's call this element A, so this element will become integral over R. And hence, A belongs to S, because S is the set of elements in E that are integral over R. And so we conclude that alpha is equal to A over B, where A is in S and B is in R. Which means that E is the field of fractions of S. So we can state that this relation holds in this diagram. Let us state our next lemma. So in the same setting, let G be the Galois group of E over F. Then we make two claims. One, the ring S is invariant under the action of the Galois group. And two, if R is integrally closed, then for every element S in the ring S, all coefficients of the minimal polynomial of S over a field F are in fact in the ring R. The second condition tells us that if we want to check whether an element of E is integral or not, we only need to look at the monic minimal polynomial of this element. if the coefficients of this monic irreducible polynomial are in R, then the element is obviously integral. And if they are not, then the element is not integral. Let us give a proof. So we start with part 1. Let S be an arbitrary element of the ring S. Since S is integral, this means that there exists a monic polynomial G in R of X such that G of S is equal to 0. Let us act on this with an element of a Galois group. So if we apply sigma to G of S, so this is of course 0, but the coefficients of G are in R, and sigma fixes all elements of F. So from here we get that this expression is also equal to G of sigma of S. And this tells us that sigma of S is integral over R, which means that sigma of S belongs to S for all sigma in G and for all S in S. So this tells us that the ring S is G invariant. Now let us prove part 2. Let F be the minimal polynomial of S over a field F. We have that F has a root in E. So because F of S is equal to 0. And E is a Galois extension. Which means that it is normal. So F factors into linear factors over E. F of X is equal to the product over J from 1 to N, X minus Sj. And the Galois group G acts transitively on the set of roots. And by part 1, G acting on S is equal to S. And we know that one of the roots is in S. So this tells us that for all J, Sj is in S. And then by taking expansion of this polynomial, we see that all coefficients of F are in S. But by the construction of F, they are also in F. And the intersection of F with S is equal to R. Since R is integrally closed, any element of F which is integral over R is in R. And this proves that all coefficients of the minimal polynomial F are in R, and that's exactly the claim of our lemma. Next, we give the following definition. Let P be a prime ideal in the ring R. We say that a prime ideal Q in the ring S lies over P if the intersection of Q with R is equal to P. We recall that an ideal P in the ring R is called prime if the quotient ring R mod P has no divisors of 0. Let's consider examples. In the first example, as our ring R, we take Z, which sits in the field of fractions Q, and then we take the Galois extension Q by adjoining square root of -5, and here we take the ring Z with adjoint square root of -5. As an ideal P, we take an ideal generated by 7 in Z. And what we would like to describe is prime ideals in Z with square root of -5 lying over this ideal generated by 7. Clearly, any such ideal must contain the ideal which is generated by 7 in the ring S. Now, let's try to understand. Is this ideal prime? To answer this question, we have to consider the quotient of Z with square root of -5 by 7 times the same ring. Now, this quotient is the same as Z7 with a joint square root of -5. What does this mean? So this means that we take the ring Z7 of X and quotient out the ideal generated by x squared plus 5. It is easy to check that the polynomial x squared plus 5 is reducible over Z7 of X. So this factors as x plus 3 times x plus 4. Then the Chinese remainder theorem says that this ring is isomorphic to the direct sum of Z7 of X, quotient by ideal generated by x plus 3, plus Z7 of X, quotient by ideal generated by x plus 4. And what we get is the ring Z7 plus Z7. The elements of these rings are pairs of elements from Z7, and the operations are carried out component-wise. Clearly, in this ring, we have divisors of 0, because 1, 0 times 0, 1 is equal to 0. So the answer to the question whether this ideal is prime is negative. However, now we can see how we can enlarge this principal ideal to get a prime ideal. All we have to do is to factor out one of the two components. And what we get is we get two prime ideals in Z with square root of -5 lying over ideal generated by 7. The first ideal will have generators 7, and as a second generator we take an element that corresponds to 3 plus x. But x in this interpretation is a square root of -5. So this will be 3 plus square root of -5. And for the second ideal, we take generators 7 and the element that corresponds to x plus 4. Only here we will switch the sign. So this will be 3 minus x, and we get 3 minus square root of -5. To see that these ideals are prime in S, we take S quotient by Q1, and we see that this is isomorphic to Z7 of X, quotient by ideal generated by x squared plus 5, and 3 plus x. But x squared plus 5 is a multiple of x plus 3. So this is isomorphic to Z7 of X, quotient by ideal generated by x plus 3. And we see that the result is just Z7, which is a field. And this means that Q1 is in fact a maximal ideal of this ring. And so it is prime, because Z7 has no divisors of 0. And we can see that Q1 intersected with Z is precisely the multiples of 7. So we see that these are two prime ideals that lie over an ideal generated by 7 in Z. It is important to point out that the Galois group of this field extension, which is a group Z2, will interchange these two prime ideals. As a second example, which will be important for us, we take the elliptic curve y squared is equal to 6 times x cubed minus x. Here is the graph of this elliptic curve, and as our ring R, we take the ring of polynomials over real numbers. F will be the field of fractions of R. So these will be rational functions in variable x. The ring S will be polynomial functions on the elliptic curve E. So this will be the ring of polynomials in two variables, quotient by the ideal generated by the equation of the elliptic curve, y squared minus 6 x cubed minus x. And as a field E, we take rational functions on this elliptic curve. So this is the field of fractions of the ring S. From this description, we see that the field E is an extension of the field F with an element y. And element y satisfies a quadratic equation over the field F. So this means that the degree of this extension is equal to 2. And moreover, we see that y is integral over R, because y satisfies a monic equation of degree 2 with coefficients in the ring R. Now first we consider an ideal P generated by x minus 2 in the ring of polynomials R of x. This is certainly a prime ideal because the quotient by this ideal is just the field R. Note that the principal ideal generated by x minus 2 in the ring S, so this is x minus 2 times S, is not a prime ideal in S. This can be seen from the following equality, that y plus 6 times y minus 6 is equal to y squared minus 6 x cubed minus x plus 6 times x minus 2 times x squared plus 2x plus 3. If we quotient out the principal ideal generated by x minus 2 in S, then the right-hand side will turn into 0, and we will get divisors of 0 in the quotient. Geometrically, this means that if we intersect the elliptic curve with a line x is equal to 2, then we will get 2 points of intersection, y equals 6 and y equals negative 6. And then this quotient ring may be interpreted as a ring of functions on a set of 2 points. But the ring of functions on the set of 2 points is R plus R, and this ring will have divisors of 0. So to get a prime ideal in S containing x minus 2, we need to remove one of these 2 points. The first prime ideal lying over x minus 2 will have generators x minus 2 and y minus 6. And the second ideal will have generators x minus 2 and y plus 6. The first ideal corresponds to the point on an elliptic curve with coordinates x equals 2, y equals 6. And the second ideal corresponds to the point with coordinates x equals 2 and y equals minus 6. So we can see that the quotient of S by each of these ideals is isomorphic to the field of real numbers, which tells us that these ideals are indeed prime. The Galois group of this field extension has order 2, and again we'll interchange these two prime ideals. Next, let us look at prime ideals in S lying over the ideal generated by X in the ring of polynomials R of X. First, let us check whether the principal ideal X times S is prime in S. So for this, we take the quotient S, quotient by ideal generated by X in S. So this will be the ring R of XY, quotient by ideal generated by y squared minus 6x cubed minus x, and also by x. But then this is the same as the quotient of R of xy by ideal generated by x and y squared, because then we can drop x cubed minus x since we already have x as a generator. And so this is the same as R of y quotient by ideal generated by y squared. And here we see that in this ring we have divisors of 0, because y times y will be 0 in this ring. So this tells us that this principal ideal is not prime. However, from this calculation it becomes clear how to lift the ideal generated by X to a prime ideal in the ring S. And we see that the prime ideal here in S that lies over X will be the ideal Q with two generators, X and Y. Geometrically, this corresponds to intersecting the elliptic curve with a vertical line x equals 0. And here we have a single point of intersection, which is the origin. And so the corresponding ideal will be the ideal generated by x and y. And we see that in this example, there is a single prime ideal that lies over the ideal generated by x. Finally, as an ideal in R, let us take ideal generated by x plus 2. And let us lift this ideal to a prime ideal in S. So again, we begin by considering the principal ideal. So we take x plus 2 times S. And we want to answer the question whether this ideal prime. Let's consider the quotient S, quotient by the ideal generated by x plus 2. So this is the quotient of R of xy by the ideal generated by y squared minus 6x cubed minus x, and the second generator is x plus 2. Since we have x plus 2 as a generator, this tells us that we can eliminate x by making substitution x equals to negative 2. So this quotient ring is isomorphic to R of y, quotient by the ideal generated by y squared plus 36. The 36 comes from evaluating x cubed minus x at x equals negative 2. And we see that the polynomial y squared plus 36 is irreducible in the ring of polynomials with real coefficients. And this quotient is isomorphic to the field of complex numbers. So this means that we have no divisors of 0 in this quotient, and the answer here is positive, that this principal ideal is indeed prime. Geometrically, this means that we have no points of intersection of the elliptic curve with the vertical line x equals negative 2. And this intersection will only have complex roots. So the answer to this problem in this case is that there is a single prime ideal in S that lies over P. And this is a principal ideal generated by x plus 2. Next, we state a theorem that claims that we can always lift a prime ideal in R to a prime ideal in S. Theorem. Let S be integral over R, and let P be a prime ideal in R. Then there exists a prime ideal Q in the ring S lying over P. Let's give a proof. Let us set M to be the set R without the prime ideal P. Since P is prime, this tells us that M is closed under multiplication. Because if we have two elements that are not in P, their product will also be not in P. Otherwise, we will get divisors of 0 in the quotient ring. Using Zorn's lemma, choose a maximal element Q in the set of ideals in S which do not intersect with M. So this means that Q intersected with M is empty set, and Q is maximal among ideals with this property. Zorn's lemma is applicable here because if we have a nested family of ideals that do not intersect with M, then their union will be again an ideal that does not intersect with M. Our first claim is that Q is a prime ideal in S. And we prove this by contradiction. So if ideal Q is not prime, then there exist A and B in S such that A and B are not in the ideal Q, but the product A times B is in the ideal Q. Consider now a big ideal that is generated by Q and an element A. This ideal is strictly bigger than ideal Q because A is not in Q. By maximality of Q, this intersection with M is now non-empty. So this is by maximality of Q. Likewise, an ideal generated by Q and B also has a non-trivial intersection with M. Now let S1 be an element of the intersection of Q with A intersected with M, and S2 be an element of the intersection of the ideal generated by Q and B and the set M. Then the product S1 times S2 belongs to M, since M is closed under multiplication. And also this product belongs to ideal Q, since A times B is in Q. So this tells us that the intersection of Q with M is not empty, and this is a contradiction. Because by construction of Q, this intersection it was empty. The source of this contradiction was our assumption that Q is not a prime ideal, so this proves that the ideal Q is in fact prime. Our second claim is that the ideal Q lies over P. So this means that Q intersected with R is equal to P. By construction, we know that Q intersected with M is empty, and M was R without P. This tells us that Q intersected with R must be inside P. And to prove this equality, we only need to show that P is inside Q. Let us prove this by contradiction. Suppose X belongs to P, but does not belong to Q. Consider the ideal generated by Q and X. Then, by maximality of Q, this intersection with M will be non-empty. By maximality of Q. And let little m be the element of this intersection. Then this element m may be written as Q plus X times S, where Q is an element of the ideal Q and S is an element of the ring S. So we know that element S is integral over R. This means that we can write a monic polynomial for which S is a root. So we have S to the power n plus R n minus 1 S to the n minus 1 plus R1 S plus R0 is equal to 0, where Rj's are elements of the ring R. Next, we multiply this equality by x to the power n and then take everything mod q. In particular, we will have that m is x times s mod q. Then, if we multiply the left-hand side by x to the power n, we will get m to the power n plus x times r n minus 1 m to the power n minus 1 plus dot 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 plus r1 times x to the n minus 2 times m plus r0 times x to the n minus 1, and this whole thing is in Q. Now let us analyze this. So M is an element of the set M, which is a subset in R. X is in ideal P here, which is also in R. So this tells us that the left-hand side is in fact in the intersection of Q with R. So here the first factor, X, is in P, and the second factor is in R. So this tells us that m to the power n belongs to P plus Q intersected with R. But we already proved that Q intersected with R is in P. So this means that this is equal to P. But P is a prime ideal. And if m to the power n is in P, this tells us that m is also in P. But what was our definition of the set M? M was R without P. And here we proved that we have an element of this set which is in P. So this is a contradiction which shows that P is a subset of Q, and this proves that Q is a prime ideal of S that lies over P. This completes the proof of this theorem. Our next result tells us that we cannot have nested ideals in S lying over the same ideal in R. Proposition. Let S be an integral ring extension of R. Suppose Q is inside A, so be ideals in S, and Q is prime. If these two ideals have the same intersection with R, then they're equal. We prove this by contradiction. So suppose S is an element of A which is not in Q. Since S is integral over R, so this tells us that S is a root of some monic polynomial in R of X. Let G be monic in R of X of lowest possible degree such that G of S is in Q. Such a polynomial exists because we already have a monic polynomial for which S is a root. So that is f of S will be 0. But perhaps there is a monic polynomial of even lower degree such that G of S is not necessarily 0 but in Q. And we choose G to be such a polynomial of the lowest possible degree. Let us look at this polynomial. We'll have s to the power m plus r m minus 1 s to the m minus 1 plus r1s plus r0 is equal to q, which is some element of the q. Let us move r0 to the right-hand side. Then we can factor s times s to the m minus 1 plus r m minus 1 s to the m minus 2 plus r1 is equal to q minus r0. By our assumption, q is contained in the ideal A. And s here is also an element of the ideal A. So now this left-hand side is also in A. So this tells us that element r0 belongs to the intersection of R with A, which is equal to the intersection of R with Q. So this tells us that Q minus R0 is in fact an element of the prime ideal Q. If we denote this sum as H of S, then by minimality of the degree of G, we have that H of S does not belong to Q. And here we have that S times H of S does belong to Q. And Q is a prime ideal. So this tells us that S must belong to Q. And this is a contradiction because we assumed that S does not belong to Q. And this proves that the ideals Q and A coincide. In our next lecture, we will study the action of the Galois group on the set of ideals in S lying over a given ideal P in the ring R.